and there are 2 trillion of them in a piece of the universe we can see, and we're very sure that that piece that we can see is a small bit of what may be an infinite universe beyond. We don't know, actually.
We concluded that actually the universe really isn't slowing down. It's actually speeding up in its expansion. And that was a
13.8 billion years ago, our universe began with a hot Big Bang. The universe was filled with matter, antimatter, radiation, and existed in an ultra-hot, ultra-dense but expanding and cooling state. By today, the volume containing our observable universe has expanded to be 46 billion light-years in radius, with a light that's first arriving at our eyes today corresponding to the limit of what we can measure. Its edge is about 270 quintillion miles away. To put that figure into perspective, if you drive at a steady rate of 65 miles per hour, it will take you 480 quadrillion 800 trillion years to get there. That's 4.8 times 10 to the power of 17, or 35 million times the current age of the universe. Although that's an unimaginably huge distance, it's not infinitely large. It's merely the limits of what we can observe. What lies beyond that? What about our unobservable universe? Is there any way to use what we know and measure about the universe we inhabit to answer the question of whether it's finite or infinite? About whether what we know of as the universe goes on forever, or whether there's some limit to what's out there? These questions have fascinated scientists for centuries, and now, thanks to the James Webb Space Telescope, we can peer back over 13.5 billion years to see the first stars and galaxies forming out of the darkness of the early universe, thereby unlocking the secrets of the universe. However, in addition to wowing the world with breathtaking glimpses of galaxies from cosmic dawn, the $10 billion time machine also leaves scientists scratching their heads as its discoveries challenge the perception and understanding of our universe. They raise world-shattering points about how the expansion of the universe seriously factors into the way we calculate the size of the universe. Join us today as we dig deep into what the James Webb Space Telescope has just announced as the true scale of the universe. For starters, the fact that we know the observable universe to be 93 billion light-years across is astonishing. But how do we know it? Well, the story starts out with an Australian mathematician and physicist called Christian Doppler. In the 19th century, Doppler tried to explain an unusual phenomenon about electromagnetic waves. If an observer moves towards or away from the source of a wave, the length of that wave decreases or increases respectively. This is now called the Doppler effect and was confirmed for essentially all types of waves. Imagine you're standing on a sidewalk watching cars pass by. As each car approaches you, the sound of its engine is relatively higher in pitch. However, as the car moves away from you, the sound gradually becomes lower in pitch. This is the Doppler effect in action. For astronomers, this is an extremely important point. If you have some stars you can use as a reference, a sort of cosmic candle, if you will, you can look for all sorts of anomalies in the wavelengths you're seeing. Increased wavelengths mean the object is moving away from you, or redshift, and if the wavelengths are getting smaller, it's moving towards you, or blue shift. In the 1920s, Edwin Hubble discovered something unusual. Some things are moving towards each other, and others are moving away. But in a general sense, everything seems to be moving away from everything else around it. What Hubble found was that the universe was expanding. This was truly a groundbreaking moment, a paradigm shift from the universe which was once thought to be fixed and stable. Not only that, but this universal expansion also appears to be accelerating. We still don't know exactly why or how this happens, but subsequent measurements have confirmed and refined this idea. Dark matter and dark energy are the likeliest explanation for these observations. And studying redshift is fundamental for studying cosmic distances, especially for things that lie far away. But this is where things start to get a bit tricky. If you're looking at something that's, say, 1 light-year away, you see it the way it was 1 year ago. But in that year, the universe has expanded, so the distance between you and that object is now greater than 1 year. Astronomical observations have found the age of the universe to be around 13.7 billion years, and one of the farthest objects we've ever discovered is a galaxy called GNZ11 or GNZ11. This galaxy is 13.4 billion years old, which is as old as they get. However, although it took light from it 13.4 billion years ago to reach us, the galaxy lies way farther than 13.4 billion light years away. In fact, astronomers believe it to be a whopping 32 billion light years from Earth. So, it's misleading to think that the age of the universe in years also represents its size in light years. But we can go further than that. We can detect some photons which were formed before any other star or galaxy. These earliest photons come from the so-called cosmic microwave background, or CMBR, faint cosmic background radiation filling all space. This is the earliest known electromagnetic radiation, and as far as we can tell, it's the oldest thing we can detect. Some of our most accurate estimates of CMBR come from the Wilkinson Microwave Anisotropy Probe, or WMAP, which, along with other estimates, found that the farthest observable photons come from 46.5 billion light-years away. This would mean that our observable universe is, at the very least, 93 billion light-years across, 46.5 billion light-years in both directions. We have no idea where Earth is located relative to the observable universe in general, but there's no reason to believe that we occupy a special position. At any rate, the observable universe is estimated to be about 93 billion light-years. But what about the entire universe? What can we say about the part of the universe that's beyond the limits of our observations? Is the universe infinite? Well, the blunt answer is, we really don't know. We can't observe anything outside of the observable universe, duh. So we really can't for sure know, but that doesn't mean we can't make some educated assumptions. There are different studies attempting to calculate the real size of the universe. For instance, one statistical estimate carried out by Oxford researchers found that the universe might be 251 times larger than the observable universe, which would put it at 23,343 billion light-years across. That's on the conservative side. One study reports that the universe is 10 to the power of 10 to the power of 10 to the power of 122 megaparsecs across, with 1 megaparsec being 3.26 million light-years. That's a number so big there are no reasonable units of measurement that can adequately express it. Whether you express it in meters or light-years or megaparsecs, the difference just gets lost in the final digits. If the universe were to be this big, then even if it's not technically infinite, it could still be practically infinite. Nothing from our location could reach its edge or vice versa. But it gets even weirder. Remember, we live in an expanding universe. We know that from Hubble, but Hubble was off on his initial measurements. Recent studies have converged on an expansion rate of around 70 kilometers per megasecond. So, if something is 1 megaparsec away, it's moving away at a rate of 70 kilometers per second. If it's 2 megaparsecs, it's recording at 140 kilometers per second. At 3 megaparsecs, it's 210 kilometers per second, and so on. Let's do a gross simplification. The observable universe is 93 billion light years across, right? That's 28,500 megaparsecs. This would mean that the points which are farthest away are receding at a speed of about 2 million kilometers per second. That's almost 10 times higher than the speed of light. But the theory of special relativity tells us nothing can move faster than the speed of light. So what gives? Well, technically the universe isn't moving. It's not like something is moving at 2 million kilometers per second. Space itself is expanding at that rate. General relativity does a better job of dealing with this type of conundrum, but even general relativity is, in a sense, a local law, with local being limited to our universe. We have literally no idea what's going on outside the universe, if such an outside even exists, or if there is any boundary. Furthermore, notice that the expansion rate is expressed as speed per distance. So while cosmic objects are getting farther away from one another, they aren't moving away from one another. But if you were to try to reach these faraway places, you'd have to travel faster than the speed of light, which is impossible according to our knowledge. You can even calculate that objects farther than 4,740 megaparsecs are moving away at a rate higher than the speed of light and could therefore never reach one another. Galaxies closer than that are still emitting light that can reach us. Of course, this all relies on the assumption that the universe will continue to expand indefinitely, which we may or may not know to be true. The universe could stop expanding and start collapsing on itself for all we know, or it could expand faster and faster forever. So, if the universe is not theoretically infinite, from a practical point of view, it quite likely is. But that still doesn't really answer the question, does it? The universe may be infinite, but we can only analyze a finite part of it, that part in which light has had time to reach us. As far as we can see, there are galaxies in every direction with no sign of slowing down. We've seen no sign of an edge to the universe. One argument attempting to debunk an infinite universe says that during the Big Bang, the universe was condensed into an infinitesimal point. So, how can something infinite derive from something finite? This, however, relies on an incorrect assumption. The Big Bang wasn't an eruption in space. It was an eruption of space. Before it, space did not exist, so something could not be big or small. It was a point of infinite energy, which, again, doesn't do much to clear up whether the universe can be infinite or not. Let's approach things another way. If the universe is expanding, what is it expanding into? Well, as far as we can tell, it's not that the universe is expanding into something. Space itself is expanding. In other words, it's not like the edge of the universe is always moving forward, but more like all points in the universe are moving apart. Think of it like raisins in a dough. You put it in the oven, and all the raisins are pushed apart by the expansion of the dough. But still, if the universe is finite, then it probably has an edge and an outside. What those things would be like, however, we really don't know. Here's another intriguing question. If the universe really is infinite, does that mean there's an infinite number of yous out there? Are there different variations of you, like one in which you have cat ears, and another one in which you're immortal. That may very well happen, surprisingly enough, but it's not that simple. The odds of someone exactly like you are infinitesimal. From a cosmic standpoint, the odds are so small that they're essentially zero. If the universe is infinite, then the odds of a new you are basically infinity times zero, a type of problem that has haunted mathematicians for centuries. 0 times infinity equals, huh? For the less math-savvy of you out there, this is a type of indeterminate problem. On one hand, the answer should be 0 because everything multiplied by 0 is 0, right? But on the other hand, the answer should be infinity because everything multiplied by infinity is infinity. The answer relies on how zero that 0 really is, how infinite that infinity really is. In our practical case, we don't know how infinitesimal the odds of evolving a specific life form are, so the problem remains indeterminate. You could be the only one of you out there, or there could be an infinite number of variations. It's also possible that there's a finite number of yous out there, which makes it even weirder. You've probably realized that there are a lot of ifs, maybes, and we don't knows in this conversation. That's just the way things are right now. We're still only starting to scratch the surface of cosmic truths. There's no clear-cut answer to whether the universe is finite or infinite or not, but in this case, the reward is in the journey, not the destination. The one thing we do know is that the universe is big. It's a big, mysterious place, equally wondrous and terrifying. And the fact that we, the results of stardust and physical forces, are trying to understand its nature is equally wondrous and equally terrifying, I'll admit. Regardless, one thing is for sure: our universe has a beginning, and someday it will have an end too. Indeed, according to science, there are 4 ways that our universe might actually end. Notably, the ultimate fate of the universe depends on 3 things: the universe's overall shape, its destiny, and the amount of dark energy that exists. The first 2 scenarios hinge on the universe existing in a flat or open system, one that is negatively curved, similar to the surface of a saddle. Our universe is expanding. It happens because of a mysterious form of energy that we know as dark energy. We don't know what it is, but each year this dark energy causes the rate of expansion to increase. One theory of our ultimate end relies on the assumption that this expansion will continue indefinitely, until the galaxies, stars, planets, and matter, even the subatomic building blocks that comprise all matter, can no longer hold themselves together, at which point they simply rip apart. This theory is called the Big Rip. Whether or not this actually happens depends on critical density, the boundary value between open models that expand forever and closed models which recollapse. According to Robert Caldwell, a theoretical physicist from Dartmouth College, if the Big Rip won out over all of the apocalyptic scenarios put forth in this piece, the event would occur in some 22 billion years, when the Sun has already transitioned from a main sequence star to a red giant, incinerating Earth as a result, and then into a white dwarf. If Earth did not manage to survive intact, spoiler alert, it won't, then the planet would explode about 30 minutes before the grand finale. Another popular scenario for the end of the universe that relies on deciphering the true nature of dark energy is the Big Freeze, also referred to as heat death or the Big Chill. In this scenario, the universe continues to expand at an ever-increasing speed, As this happens, the heat is dispersed throughout space while galaxies, stars, and planets are all pulled farther and farther apart from one another. In the very distant future, intelligent civilizations will look into the sky and think they are alone. Everything will be so far away that the light from distant stars and galaxies can never reach them. Eventually, planets, stars, and galaxies would be pulled so far apart that the stars would eventually lose access to raw material needed for star formation, and thus the lights would inevitably go out for good. It will continue to get colder and colder until the temperature throughout the universe reaches absolute zero. At absolute zero, all moving stops. Nothing can exist in such a place, as there is literally no energy. None. Not at all. This is the point at which the universe would reach a maximum state of entropy. Instead of fiery cradles, galaxies would become coffins filled with the remnants of dead stars. Many scientists, astronomers, and physicists alike believe this is one of the most probable scenarios. The third way that our universe might end is called the Big Crunch. It is thought to be the direct consequence of the Big Bang. In this model, the expansion of the universe doesn't continue forever. After an undeterminate amount of time, possibly trillions of years, if the average density of the universe was enough to stop the expansion, the universe would begin the process of collapsing in on itself. Eventually, all of the matter and particles in existence would be pulled together into a super-dense state, perhaps even into a black hole singularity. Such an event might have already happened before. Some scientists have theorized that the universe we see is the result of a cyclic repetition of the Big Bang, where the first cosmological event came about after the collapse of a previous universe. This is something called conformal cyclic cosmology. Unlike the first two scenarios, this model relies on the geometry of the universe being closed, like the surface of a sphere. An event like this would be like a single breath. The universe would breathe out the Big Bang and breathe in the Big Crunch. This could also happen if we see a reversal of dark energy's current expansion effect. Similar to this theory and the Big Bang is the Big Bounce. A sort of symmetry is proposed here. The universe is in a continuous cycle of expanding out and then collapsing onto itself. Effectively, we could be one of many iterations of the universe. Perhaps even more eerie to think about is the idea that maybe each time the universe resets, it plays out the same way. Perhaps the you that is currently listening to this or reading this article right now is just one of you out of the 10 to the greater Googleplex versions that existed before. Who knows? Ultimately, the universe may be like the mythical phoenix. Its death is actually a fiery rebirth. The last scenario here is named the Big Slurp. This theory surfaced just a few years ago, after revelations were released about the true nature of the Higgs boson, which is the particle that plays a role in granting mass to elementary particles. In this model, if the Higgs boson particle weighs in at a certain mass, it could indicate that the vacuum of our universe may be inherently unstable, perhaps existing in a perpetual metastable state, something that has been discussed at length many times before. If this were the case, our universe might experience a catastrophic event when a bubble from another alternate universe appears in ours. If this bubble exists in a lower energy state than our bubble, the universe could be completely annihilated. In essence, it would cause all the protons in all matter in our universe to decay. By proxy, so would we. Now, if that doesn't sound unpleasant enough, this sort of a vacuum metastability event could happen at virtually any moment, anywhere in our universe. The bubble could pop over and start expanding at light speed until it swallowed us entirely. Lovely thought. Well, truly, none of these scenarios sound fun. But again, they're all possibilities. Well, that's all we have for you today. Thanks for watching and thanks for listening. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit that like bell so you never miss out on any future episodes. And be sure to tell us what you think of today's content. Everyone's support motivates us to continue delivering quality content and to always improve. And as always, thanks for watching, and we'll see you next time.